Now let's look at a couple of examples where we will be given a system of particles. So a system of particles being at least more than one particle, and we will have to relate forces with the acceleration. So the general method that I have provided to you for solving problems in this module would continue to apply. So you can use that method for individual particles, but you can also use that method for the system of particles. The only difference would be that if you pick more than one particle, you would draw a free body diagram of that system where the two particles are together, and you will not show internal forces in the system, and then accordingly you will write your Newton's second law. If you choose to draw free body diagrams of individual particles, then you can write Newton's second law for individual particles. So you'll essentially be repeating the same thing for multiple particles. So in this particular problem, we have a pulley system, as you can see, and we have a couple of blocks. We have a pulley housing, and each of those seems to have some mass. So let's read the problem. The pulley system is designed to lift a heavy load at A, or alternatively, though not equivalently, by pulling on the cable at P. So we have A here and we have P here. So you could put a load over here, or you could pull it down with a certain force, let's say Fp, but of course both of them are not going to lead to the same result, although the effects would be quite similar, which is that the A would be raised. Assuming that the payload A has mass ma, so we know the mass of this, and the pulley housing B, which includes the pulley, has mass mb, so this has some mass too. Determine the acceleration of A and P if a mass mp is attached at P. So we have mp as well. So we have three particles. So we have ma, we have mb, we have mp. Those are the masses of the three particles, and we're looking for acceleration of A and P. Okay, so let's start by writing what is given to us. So given is mass of A, mass of B, and mass of P, and of course there are some implicit information, that is that this is an inextensible cable system. So we have two cables over here. We have cable H, we have cable G, right? And each of those cables will impose geometry constraint. We've seen that in the kinematics module for problems like these, where we wrote the length of the cable in terms of the position variables, and then we applied the kinematic analysis. So we'll start by doing that. So first of all, the coordinate system, right? So I'm going to fix the origin of my coordinate system right at the ceiling, and I'll call this to be my positive y direction. This could be my positive x, but it doesn't matter because nothing is moving in the x direction. Okay, so what about position variables? So we have y sub p, we have y sub a, and then we also have position of b. We'll call it y sub b because the pulley housing B is going to be moving up and down. All right, so we have two cables. So let's start by writing the length of each of those cable. So cable H, so cable H has a length, let's say L sub H, and that is equal to YA minus YB, right? And that's constant, so we can differentiate it twice, and I will get acceleration of A minus acceleration of B equal to 0, which means acceleration of A is same as acceleration of B. And that's not surprising, right? Because A and B are kind of rigidly connected with each other if you assume cable H is inextensible. What about other cable G? So for cable G, let's say the length is L sub G, and that would be equal to, okay, I need to show this to you. So we have YB plus another YB, 3YB, 4YB, and then we have YP, right? And all these lengths over here, which wraps around the cable, around the pulleys, are constant, so they are not important. So we have 4YB plus YP, and that's constant too. So I can differentiate it, and I will get this. And since AA is same as AB, I can write this as 4AA plus AP equal to 0. The reason I am doing that is because I'm not interested in the acceleration of B, because the question is not asking for it, right? Okay, so let's call this equation 1. Now, if this was a kinematics problem, you would end over here, right? Which means that to really be able to solve for acceleration of A or acceleration of P, you would have to be given at least one of them. Then only you'll be able to tell the other acceleration, right? Which means that now, to be able to solve this problem further, we have to move further. So the next step after kinematic analysis, this is the kinematic analysis, is to draw free body diagrams, right? So let's start with that. So free body diagram of, let's start with A. So A, we have gravity. We have the tension in the cable edge, we'll call it T sub edge of B. We have this pulley system, we have the tension T sub edge, right, because this cable connects both A and B, and then you're going to cut it here, right? So this is your B, so you draw this imaginary boundary, so it cuts in 4 places, so you have tension here, tension here, tension here, tension here. So that is T, 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 right? Because we are assuming there's no slack in the cable, that means the tension is going to be same. If there is slack, if there is friction in the pulley, then the tension is never same. So this is also an idealization. Okay, free body diagram of P, MPG, and then we have the tension T, right? Okay, so once we have this, oh, I forgot the weight of B, so MBG here as well. We can apply Newton's second law on each of these. So Newton's second law. So even though this is really a system of particles problem, I'm not really treating it as a complete system. I'm doing this analysis particle by particle. So for A, we have sigma F A equal to mass of A times acceleration of A. And remember, if you look at our coordinate system, downward direction is positive. So everything that is in the downward direction has to be positive. So MAG is pointing downward, so that would be written as MAG. This would be minus T sub H MA acceleration of A. Okay, for B, I have sigma FB equal to MB acceleration of B, and that is MBG plus T sub H minus 4T equal to MB times acceleration of B. And acceleration of B is same as acceleration of A, so I'm just going to write this as MB times acceleration of A. And for free body diagram of P, I have sigma FP equal to MP acceleration of P, and that is MPG minus T equal to MP AP, right? So that's equation 2, equation 3, equation 4. So we have 4 equations, which means we can solve for 4 unknowns. So let's count how many unknowns we have, right? So we have TH as one unknown. We have TH as one unknown, AA as second unknown. This we already counted. T is fourth unknown, and then T is already counted. In fourth, AP is the fourth unknown. So we have 4 unknowns, we have 4 equations, we can solve for all of them, right? Even though the problem is only asking for acceleration of A and P, as a byproduct, you will also get the tension in all of these cables. So if I had asked you for the tension in the cable, then you would have right away known that this is actually a problem where you have to relate the forces with the acceleration. But even though I'm just asking for the acceleration information, you see that you still have to do the kinetic analysis, where you have to relate the forces with the motion. Let's look at another example. This is example 3.14, where we have 2 particles, in fact 2 books, that are sliding with respect to a table and potentially sliding with respect to each other as well. So let me first draw the diagram. So we have a table. On this table, there are 2 books that are being thrown. So we'll call this book, we'll call it 1, and then there's another book called 2, and both of them of course have some masses, M1 and M2. So a pair of stacked books with the masses M1 as 1.5 kilogram and M2 as 1 kilogram. So let's start by writing what is given. So we have M1 equal to 1.5 kg, M2 as 1 kg. It's thrown on a table. The book strikes the table. The books strike the table with essentially 0 vertical speed, so they are thrown as horizontally as they could be, and their common horizontal speed is v0 equal to 0.75 meters per second. So their initial common velocity is 0.75 meters per second. Letting mu k1 equal to 0.45 be the coefficient of kinetic friction between the bottom book and the table. So between the bottom book and the table, there is friction, and the kinetic coefficient of friction is given as 0.45, and the coefficient of kinetic friction between the 2 books as µs2 and µk2. So between these two books, we have both static as well as kinetic coefficient of friction given as 0.4 and 0.3 respectively. Determine the book's final position. So we have to find the book's final position related to where they hit the table. So final positions of the books relative to their initial location and their position related to one another. So when we find the final positions, of course, we will be able to compute what the relative positions are as well. Model both the books as particles with the same initial horizontal position. Okay, so this is a problem where we have, two particles, right? And of course, clearly this calls for a Cartesian coordinate system, and we can choose our initial position to the position when the books hit the table, right? So we'll call this x and y, right? And kinematic analysis in this case is going to be fairly trivial. All we have to do is write the velocity and acceleration. So acceleration of a1 would be, let's say, call it a1 I hat, of a2 as a2 I hat as well, right? Then that's all we can really write about acceleration. We really don't know what those things are. Okay, so let's draw a free body diagram. So let's draw free body diagram of book 1 first. So of 1. So that's book number 1. We have the normal reaction on it. We'll call it N1 from the ground, from the table, and then we have M1G. Okay, and then the book is lying on top of book 1, so there will be a normal reaction from book 2 on book 1, which is going to compress it. So we show this in the downward direction, that's N2. Okay, and then we have friction forces, right? And that's where we need to pay some attention. So first of all, what is the direction of the friction force on the book 1 from the table? Well, the friction force job is to oppose the relative motion. Table is not moving. The book 1 is supposed to be moving towards the right. It has to move towards the right. It cannot come to a stop right away, because otherwise it will experience an infinite deceleration, right? Which cannot happen. So it has to move to the right with respect to the table, which means that the friction force F1 we will call would be equal to whatever the kinetic friction is given, mu k1 times the normal reaction, right? So we'll have that. Okay, what about between book 1 and 2? Well, there is the friction between those two books as well. So do we know whether book 2 is going to slide with respect to book 1, or book 2 is going to stay with book 1, right? Those are the only two possibilities. So either it stays with book 1, which means there is no relative sliding between the two, or the book 2 slides, right, with respect to book 1. So let's start by assuming that there is no sliding. Now, typically, whenever you are faced with a dilemma like this, where you have to choose between the two possibilities and you don't know for sure what is going to happen, you can choose any possibility to begin with, whatever makes sense to you. You can start with that and then compute everything according to that assumption. And if your final result is consistent with your initial assumption, then everything checks out. But if the final result is in contradiction with your initial assumption, then you know there is a problem. So just to give you some idea, we will start by assuming that the book 2 doesn't slide with respect to book 1. Okay, so if it doesn't slide, then there has to be a friction force between the two that will oppose that relative motion, which means that that friction force has to have an upper limit, and we know what that upper limit is. Upper limit on any friction force is the static friction force. But if you find out that your friction force actually exceeds the static friction force, that means you know there is a problem, right? Okay, so that's what we are going to do. That will be our check for this calculation. So we are assuming that book 2 does not slide with respect to book 1. So let's write that. So assumption is that book 2 does not slide with respect to book 1. Okay, so if the book 2 is not sliding with respect to book 1, then what should be the direction of friction force on book 2. Now remember, we have not finished the free body diagram of 1 yet, right? So let me just move on to free body diagram 2, and then we will know exactly what the friction forces are on 1 from 2. So this is our book 2. So we'll have the normal reaction, which is N2. We'll have the weight, okay? Now, if the book 2 is not sliding with respect to book 1, then the question is, should it be pointing in the forward direction or in the backward direction? Well, both the books are going to come to a stop eventually, right? Because of the friction. And that means that the acceleration that each of them will face will be actually a deceleration, right? And where would that deceleration come from? From an opposing direction force, which means that the friction force on 2 from 1 should really be in the backward direction, right? And if now the friction force on book 2 from 1 is in the backward direction, that means that the friction force on 1 from Newton's third law from the book 2 would be in the forward direction, right? So that gives you the free body diagram. And our assumption is that the book 2 does not slide with respect to book 1. And of course, we have to make sure that this friction force, F2, is going to be less than or equal to mu(s) times the norm of N2, right? It has to be less than that because that is the upper limit. Mu(s) times N2 is the upper limit of friction force anywhere, okay? All right, so we have the free body diagram. Now we can apply Newton's second law, okay? Since I have a space over here, I'm going to use the space to actually do that analysis. So sigma F on 2 equal to mass of 2 times acceleration of 2. So we have F2 minus F1, that's along I hat direction, plus N1 minus N2 minus M1. This is actually book 1, right? Yeah, so this is book 1, so I shouldn't really write this as 2 here. This is 1. Sigma F1 equal to M F1. This is 1, 2. Sorry for this mess. Okay, so sigma F1 equal to M1A1 minus M1G time equal to M1 times A1. Okay, and this is along J hat direction, and A1 is entirely along I hat, right? So that gives us F2 minus F1 equal to M1A1, and we get N1 minus N2 minus M1G equal to 0. So those are the two equations we get from that. We can do the similar analysis for 2, which is sigma F2 equal to M2A2. So what are the forces on 2? We have minus F2 I hat plus N2 minus M2G J hat equal to M2 A2 I hat. So that gives us N2 simply as M2G and F2 equal to minus M2 A2. That's number 4. Okay. All right. Now, if we assume that the book 2 does not slide with respect to book 1, what does that tell us about the acceleration of 1 and acceleration of 2? Well, they have to be same, right? So this implies that acceleration of 1 should be acceleration of 2 because they're moving together, right? Which means that we really don't have A1 and A2 as separate unknowns. They're essentially same, right? Okay. So let's see if we can find all of these accelerations as well as the friction forces, right? So F2 is known to us from here, and A1 is equal to A2. So F2 is also equal to minus M2 A1 from equation 4, right? So I'm going to substitute this in equation 1 right over here. So that's minus M2 A2 minus F1 equal to M1 A1. So that gives us F1 equal to minus M1 plus M2 times A1. Okay, and we also have N2 from here, right? So we have N2 over here, so we are going to substitute this N2 in equation number 2. So if I do that, what do I get? N1 equal to M2G plus M1G, so that's M1 plus M2 times G. So N1 is known, so let me write this, the things that we have just found. N1 is M1 plus M2G, which is completely known. N2 is equal to M2G, right? So you know that as well. What else we know? Well, we also know that f1 is actually nothing but mu k1 times n1, right? So we can get that as well. We have f1 right over here. We have also substituted f1 in the equation number 1 and gotten this as a result, right? Okay, so let's substitute mu k1 n1 f1 in here, right? So if we do that, what do we get? Mu k n1 equal to minus m1 plus m2 a1, and n1 is m1 plus m2g equal to minus m1 plus m2 a1. So that gives us a1 equal to, this cancels as mu k times g. And the negative sign essentially indicates that it's actually a deceleration, because we have assumed the right hand side direction to be positive. This is positive x direction. So this is telling us that acceleration a1 is actually a negative quantity, right? Okay, so we get the acceleration. Now the only thing we have to find out is the f2. So f2 is equal to minus m2 acceleration of 2. Acceleration of 2 is same as acceleration of a1, so that is minus mu k g. So that gives us mu k times m2g. All right, so we also want to ensure, so actually at this point we know everything, right? So we know acceleration, we know the forces of friction, we know all the normal reaction. So let's apply this test. This is the test that says that this should be less than or equal to mu s times the norm of n2, right? And the norm of n2 is m2g, so let's substitute that. So the relationship becomes mu k times m2g should be less than or equal to that. These two cancel. So mu k should be less than or equal to mu s. That's the condition, right? So this mu s actually is mu s2. This is mu s2. Mu s2, right? Right over here. And the mu k that we are writing here is actually mu k1. So I should write that. This is mu k1 because that's from the book 1. So mu k1 should be less than or equal to actually mu s2. Is that the case? So mu k1 is 0.45 and mu s2 is 0.4, which means that this is not true, right? This is not true. So that means that this assumption that we made over here is also wrong, because what we have computed is not consistent with our assumption. Now, if it turned out that this was okay, then we wouldn't have to go any further, right? But that is not the case over here. So what do we do in this case? Well, we have to go back. We have to go back over here and we have to disregard this assumption now. So we have to assume that that is no longer true, which means that the book 2 does slide with respect to book 1, and that means that this won't be true anymore, right? Acceleration of 1 would not be equal to acceleration of 2. So we would actually lose on that equation, because the two accelerations won't be equal to each other, but we will gain somewhere. Where are we going to gain? Where we are going to gain is in the nature of this friction force F2, right? Because now we will assume that book 1 and book 2 are slipping with respect to each other. This friction force actually will become mu k2 times n2. So yes, we will lose on the relationship between their acceleration, but we'll gain on knowing what the friction force is, right? So free body diagram doesn't change. The equations that you have written over here, 1, 2, 3, and 4 don't change also. So what will change is that you will not equate, so all this stuff that we did after that, right, all this stuff is now going to be valid, because acceleration of a1 would not be equal to acceleration of 2. So what would happen over here is you will write, so now we go back to assume slip between 1 and 2. So now a1 is not equal to a2, okay, but f1 is equal to now mu k1 times n1, f2 is equal to mu k2 times n2. That's the basic difference that we get now, right? Because now we will know what f2 is. And with these known, then you solve for a1 and a2 and a3 and a1 and a2 and other quantities from the 1, 2, and 3, 4 equations. And in this case, if you do the calculation, everything should check out, because if it doesn't, then we have probably made a mistake in the calculation.